We're going to take a look at quantitative analysis in equilibrium systems. So something we've already discussed is K, which is the equilibrium constant and exists at equilibrium. And of course, K actually depends on the conditions of the system, which is a system of gases at a particular moment. But these changes, but K can change depending on if the conditions change. So K is probably, even though K is calculable at equilibrium, it can change depending on the change of the system. So if you know the information at equilibrium, you can calculate K. Other than that, K will be given. Most systems will not be at equilibrium moving forward. So we do have a way to at least calculate and compare and see if a system is at equilibrium or not, and it's called Q, the reaction quotient. So what we do with this is we take the concentration of reactants and products at a certain point, and we plug them into the aforementioned K equation from the past, and you can actually calculate and compare. So if we have a general equation as this one, to calculate Q, it's going to be products over reactants. And again, this is the exact same thing we would have already done to calculate K, or to calculate K, depending on its equilibrium. So of course, Q is going to give us the concentrations at any particular point. At equilibrium, the two are going to be equal to each other. So we sort of have three outcomes. If K is greater than Q, then the system shifts to the right. And the way I've designed this equation here is to show that the arrow is pointing this way, and that would be pointing that way to the side of the products. Number two, if they're equal to each other, then the system's already at equilibrium. And if 3, K is less than Q, the system shifts to the left. Again, the arrow is pointing the direction of which the system will shift, shifting to the reactants over here. So let's take a look at an example, and there's sort of a picture to go along with this example. The key parts is we've got our reaction, and it's between gas A and B, and it says at equilibrium we have the concentration of A and the concentration of B, and since this is at equilibrium, our first step is we're going to be able to calculate K. Then what we're going to do is we're going to look at these pictures here, and these are 4 different questions. From these, we're going to calculate Q, and then we'll be able to compare the two values and decide which way our system is going to shift. So we're going to calculate K, and then we'll calculate Q and compare to our known K value. So right off the bat here, to calculate our K, the equilibrium conditions were those two values. Divide them out, you get 0.43. So when our system's at equilibrium, it's got a K constant of 0.43. So for us to be able to calculate Q, we're simply going to have to count the red and blue spheres. The way this one is set up, we've got our, again, it's our products over our reactants. The blue are the products, and the red are the reactants. So the red's going to go on the bottom the whole time, blue's going to go on the top. So to calculate Q, you count 8 blues, you got 2 reds. That equals out to 4. So we can compare 4 to 0.43. So clearly K is less than, right? 0.43 is less than 4. So this must mean, if our arrow is going that way, that it's going to point and process to the left or the reactants. Number 2. Again, blue on top, red on the bottom. Count the blues. We get 3. You get 7 reds. Divide those out. It's 0.43. The two are equal to each other. So this system here would be at equilibrium. Number 3, this time we have 4 divided by 6, which is 0.67. So 4 blue divided by 6 red. And in this case, K is bigger, so it's going to point to the left, and our reactants will be favored to make more of those red ones. And in our last scenario here, we've got 2 divided by 8. Blue divided by red is 0.25. So K is just slightly bigger. And so this time our system is going to shift towards the product side to make more blue ones. Let's take a look at another example here. So we've got a reaction, and we do have a 2 involved this time. And at equilibrium, we've got a K value of 0.21. So we don't know if we're at equilibrium in this reaction. So we've got 2 concentrations given. So we're going to figure out here, are we at equilibrium or which way is this system going to shift? So the plan first is we're going to set up our Q. So our Q is our reactants over our products. Those are the reactants. They're going there. There's a 2 here, right? That's going to become our exponent. And then this thing goes in that spot there. We are given the two concentrations, 0.55 and 0.12. So we're going to square that 0.55. We're going to divide by 1.2. We get 2.5. So we can now compare our Q value to our K value. It looks like Q is going to be bigger. So K is less than Q. That is now the direction we're pointing to the left. So it looks like this side of our reaction is going to be favored and our system's going to shift to make more of that. And if you have access to these questions, please do them.